Everybody. I'd love to introduce Feliciano Giustino from UT Austin, and yep, he's been modeling semiconductors at a very atomic scale and doing those simulations. Yeah, welcome, Feliciano.
So thank you for the invitation, Greg. So again, my name is Feliciano Giustino, and I'm from the University of Texas, Austin. So what I would like to tell you today about is some work that we've been doing in order to try and support work on the design of new transistors one atom at a time. So just before I start, let me tell you where I work. So here you see UT Austin as my main affiliation, and then there are two units. So the Odin Institute and the Department of Physics. So I'm sure everybody knows what is the Department of Physics, but maybe you're not familiar with the Odin Institute. So I have just one slide to introduce that. So the Odin Institute, so the long name is Odin Institute for Computational Engineering and Sciences. So we are a unit within the University of Texas that is mostly focused on research and where we emphasize interdisciplinarity. So what that means is that we have people working across the board from, let's say, physics to mathematics to even medicine and geosciences. And the common denominator is that we are all interested in applied math, computing, high-performance computing, algorithms, and code development. So we do have a graduate program. So if anybody is interested, we admit about 30 students every year with a very strong focus on, let's say, coding and algorithms and applied math. And we work with many other departments. So in my case, for example, I'm spend half of my time in the institute and half of my time in the Department of Physics. So what we do in my group, I guess, can be summarized in about 3 slides. So the first thing is that we are interested in the quantum theory of materials. So what that means is that we try to describe the behavior of materials at the level of individual atoms using quantum mechanics. And here you see just a pictorial representation of a wave function in a material for solar cells. To do that, we develop software that is used on high-performance computers. The picture you see on the left is a photograph of the Frontera supercomputer that is sitting here at the University of Texas, in particular the Texas Advanced Computing Center, which is the flagship supercomputing center of the National Science Foundation in the US. And we use these techniques to essentially try to support the design of new materials. And that means that we had to talk to experimental colleagues. And on the right in this image, what you see is just a powder. I mean, if you look at the vial here, this powder actually is a set of microcrystallites of a material that we predicted on the computer and then was subsequently realized and now is used commercially by many research groups. So what I would like to tell you about today is about the work that we've been doing in the area of microelectronics. And the motivational slide is something that probably this community is familiar with, which is the cost of training large language models. So this slide is just to say that there is a lot of need for more compute power, but also for more efficient computing. And to motivate that, let me just emphasize a couple of numbers. The GPT-3 model, so the one from last year from OpenAI, required so in order to be trained, required enough energy to consume about 500 tons of CO2 equivalent. So that's a lot of energy if you compare to what we spend as humans in 1 year of our lifetime. We spend about 5 tons, so about 100 of this amount. And this is not the end of it. It's actually more like the beginning. If you just look at the numbers for GPT-4, these are just estimates. They're not released yet. But GPT-4 has about 10 times more parameters than the version 3. And to train that, it takes about 20,000 tons of CO2, which is about 1 year of energy for 5,000 houses in the US. So clearly, the amount of computing that we need is going up, and probably is going up much faster than what we anticipated a few years ago. And that means that there is a strong need for developing new devices and new concepts for computing in order to make this development of data-driven science and engineering possible, but also sustainable. So this chart that you see here is something that is pretty common in the world of electronics, is essentially a timeline of development of electronic devices, in particular transistors. I will explain in the next few slides. And this is just for over the past maybe 20 years. So what this timeline is indicating, these little numbers, 90, 65, 40, 28. So this is nanometers, is the essentially the characteristic size of the transistor that is in the chips that we use. The main problem is that we reach a size of the order of a few nanometers, and at this size, the standard scaling, which means reducing the size of silicon-based devices, is not working anymore. So there are many options to go around this problem. So the electronics community is investigating many directions. For example, some of you might have heard of neuromorphic computing strategies. There is also something more related to fundamental science, like quantum computing or quantum technologies. And maybe the one that seems to be the most promising at this point, at least for immediate or near-term applications, is this branch down here, which is essentially trying to scale existing transistors based on silicon without changing the concept, but changing the materials. And the materials that people have been considering are two-dimensional materials that are introduced in the next few slides. So now I would like to focus on this part to explain what has been happening in this space over the past actually half a century, I would say. So in this slide, what you see is a schematic of what we call the metal oxide semiconductor field effect transistor. So this is a device where you have this gray area that represents a silicon crystal. So the crystal structure is down here, where you see atomic atoms represent as spheres connected by some sticks, which will be the atomic bonds. And then the electrical current will go from the source on the side to the drain once you apply a voltage between these two sides. And in order to control this current, these devices also have this green part, which represents the gate. The gate is essentially a metal, this green thing here, separated from the semiconductor channel by a oxide, which is represented in orange in this picture. So the way this works is that while you have electron flow from source to drain, the voltage of the gate modulates this current. In the same way, you would have maybe a valve in a pipe that carries water, and with the valve you control the flow of water. That's exactly the same that happens in a transistor. So the typical electrical characteristic of transistor is the current to voltage curve, which you see here on the right. So what is happening here is that as you keep the increase in the voltage between the source and the drain, the current increases slightly, and at some point it saturates, okay? So when the current saturates, we say that the transistor is in the on state. Otherwise, we would say the transistor is off. The important part is that this plateau here that you see with numbers 0.2, 0.3, 0.4, 0.5, the height of the plateau is controlled by the gate voltage. So what is happening here is that you swing the current in transistor from, let's say, some very small value that we consider 0 to a very high value that we consider 1, and that's what enables logic operations in binary format, okay? Now, the reality is that this is a schematic that is used in textbooks, but is no longer representative of what goes on today. So this schematic, actually, this kind of layout of transistor was used until maybe 15 years ago. It was introduced actually more than, 50 years ago with the Intel 404 chip, which contained about 2,000 transistors. And the size of this object was the order of 10 micrometers, okay? So as people kept adding more transistors to the same chip, what was happening is that the size of the transistor kept shrinking, okay? And because of that, you lose electrostatic control in the channel. So the transistor characteristics degrade. In order to regain control, what people started doing is to deform the structure, and that has resulted into the evolution of what we call now the FinFET architecture. So this would be a field effect transistor, where the channel has the shape of a fin, like the fin of a fish. And this means that the gate now is on 3 sides of the channel, and this allows for better electrostatic control. So this has led to a generation of Intel Ivy Bridge chips that was released in 2012, and most of us probably used it. And this is based on what is called a 22 nanometers process, means that the feature size of this channel inside this under this bridge is basically about 22 nanometers. 22 nanometers, just to give you an idea, is about 80 atoms of silicon across. Okay, so we are really in the nanoscale, and this has enabled the use of the design of chips with of the order of 1 billion transistors. So that was 10 years ago, and more recently we had some new developments, and this is an example for the Apple Bionic chip, which was released a couple of years ago. Now this has about 16 billion transistors, and again it is even smaller. So this is a 4 nanometer process. So 4 nanometer means that you have about 16 atoms of silicon across the channel. And to have electrostatic control, what people have done is to have the gate on 4 sides. Okay, so now instead of a fin, we have something called ribbons, so very, very thin layers of bars of this silicon channel. So this essentially is this thinning, this nanoscale kind of scaling down of the channel is absolutely essential in order to maintain control on these electrical characteristics. And that's basically the direction where the whole industry is moving. So why this is becoming problematic at this point? This is becoming problematic because these transistor characteristics are starting to degrade as the size of the transistor gets smaller. So let me explain that with a simple couple of equations. So the on current, so the value of the current here, it can be shown using simple electrical engineering considerations that is proportional to a quantity called the mobility. So mobility is, we'll explain later what that is, but essentially quantifies how fast electrons can move across the semiconductor once you apply an electric field. It turns out that mobility actually is very important to determine, to quantify this current, but it's also very important to determine how fast electrons go through the channel, and therefore how fast you can switch on and off the transistor. So this essentially controls the clock frequency of your chip, if you want. So people are interested in keeping the mobility very high so that you have a low resistance and therefore low power dissipation. So the transistor should not heat up too much. But what people have found, and this was known since already a couple of decades, is that if you make the transistor channel very thin, this is an example of a thin layer transistor from 2006. What is happening is that this mobility that is supposed to be of the order of 1,000 in these units, these are centimeters squared per volt second, degrades to the level of 200 in the nanoscale and keeps going down when you reach 2, 3, 4 nanometers. So once the mobility goes below 100 in these units, you start having significant heat dissipation. So your chip heats up and you spend most of your energy essentially into electrical resistance, not really in performing computation.
So question.
Yeah, go ahead.
Is the intuition that it's the connectivity between the components is smaller? Is that why mobility gets lower?
So actually, it's the other way around. So if the mobility is lower, the conductivity is lower. Yeah.
No, I mean, like, is it a feature like is a like surface area kind of calculation? Is it a distance traveled kind of intuition, or is it more like related to the electrical field shape?
Oh yeah. I'll show you in the next slide. Yeah, good point. So you're asking why it degrades.
Yeah.
Yeah, let me just make a point that, so these were old measurements, but there is also some more recent measurements showing that even if you go down to 1 nanometer thickness, it really plummets below levels that are unsustainable. So your question is why do that happens? Actually, it's a very simple question of the surface to volume ratio. So this is just a atomic scale model of the interface between the silicon channel in these devices and the oxides that separates it from the gate, from the metal gate. So what is happening essentially is that in a thick transistor, most of the electron flow happens in this blue area. If the size, the thickness of this channel goes in the range of sub-nanometer, you are pushing most of the electrons to travel near this interface, which is disordered, and therefore you have a lot of imperfections that scatter your electrons. Okay, so the reason why at the nanoscale the mobility degrades dramatically is that the electrons are feeling too much the effect of the surfaces. Okay, so that's the main problem. And this is what motivates many groups to think about other solutions where these interfacial scattering problems are not present. So let me just explain why then people want to move to 2D materials. So two-dimensional materials is essentially materials that can exist in a form of maybe one layer or two layers or three layers of atoms, and they can sit, on top of an oxide, for example, without having, this kind of amorphous structure. They form something called van der Waals bonds, and because of that, they are relatively separated from the underlying substrate or the oxide at the top. So what that means is that these 2D materials can exhibit essentially atomically perfect interfaces, and because of that, people would expect them to carry electrons with much higher mobility and therefore conductivity. Okay, so that's basically the ball game for most of current electronics, trying to figure out how to use 2D materials to avoid this surface or interface scattering problem. Now,
so question then,
go ahead.
So you focused on the power driving the current. What about the noise of what is now a very small current, the time to bring up a current versus bring it down? How are those things affected?
So these are very good questions. So that's more like for electrical engineering. So the noise is something that has to do more with the fabrication process. So the reality is that this image that you see here is actually an idealized kind of a conceptual schematic, and making this kind of transistors is much more difficult than it may look like from this figure. So there is a problem of reproducibility. That's the main issue. Once the transistor is realized, usually there is no issue with signal to noise ratio, because the currents you can sustain are relatively large. The problem is more about the reproducibility. So you might not be able to make two transistors with the same material that exhibit exactly the same characteristics. Okay, so it's more like being able to scale up the production in a way that you have a consistent yield of devices with the same characteristics. That's the main problem at this point. Okay.
And what about the time component? So that's the material component. What about the time component of just noisy current levels and bringing material, them up and down?
Well, that's usually not. So what happens that people that's not an issue once you are working. So what happens that what people do is to essentially you don't proceed with a certain material if it does not deliver a certain on to off ratio, essentially. So of the order of I don't know, thousands or to a million. Okay, so that's a starting point, and if that requirement is not met, one just doesn't go forward. So usually, the only materials that go forward are those that deliver actually capabilities for logic operation, so that you can have a swinging current that is several orders of magnitude. Okay, so once that is done, you don't need to worry about noise, because these are all digital devices in practice. Does it make sense?
Yeah, it does. Yeah.
Okay. So just the one slide about 2D materials in case you guys have not heard about it. So we are used to materials in 3 dimensions. But we actually live without the materials in 2D around us, and the most common example is the tip of a pencil. So if you take a pencil, the tip is essentially the core is essentially graphite, and we are able to write because if you rub the pencil on a piece of paper, some graphite planes, so atomic planes, actually gets detached and remains attached to the paper, and that's what gives the mark of the pencil essentially. So this concept was exploited in 2004 by Andre Geim and Kostya Novoselov in Manchester to try and see whether you could actually find out individual atomic layers of graphite by really rubbing pencils over a surface, and they did that very skillfully using essentially a Scotch tape method, where you peel off layers of graphite one by one and you reattach them to a new surface until you end up with a single atomic layer. So this is what led to the Nobel Prize in Physics about graphene, a single layer graphite that is, in 2010. And after that, there's been an explosion of work in the world of 2D materials. So now there's been tons of 2D materials discovered. the fabrication methods have improved, have developed well beyond, using the Scotch tape. There are industrial processes, scaled up processes, and many companies, like many major players in the field are developing two-dimensional materials. So this seems to be the most promising avenue to deliver post-silicon electronics, at least on paper. So the issue that exists in this area is that if you go measuring the mobilities of a few of the most promising semiconductors in 2 dimensions, these would be these colored dots in this plot. Those are actually in the same ballpark as the degraded silicon mobility that I showed in the previous slides. So what that means is that even if they are supposed to deliver much higher mobilities because they are supposed to have perfect interfaces, the reality is that the situation is not as good as we would hope for, and therefore people are still looking for 2-dimensional semiconductors that may deliver much higher mobilities. So there is another problem, is that the silicon has been used for maybe now 70 years. So the industry and the manufacturing of that is extremely well developed. So to replace all the production lines with new materials, one will really need a big incentive, and the incentive in this case will be trying to find materials which exhibit mobilities that are maybe 10 times or 100 times better than silicon. So, and that's where what we do plays a role. So in the next few slides, what I'm going to do is to try to tell you how we perform calculations of these kind of properties, in particular the carrier mobility, and trying to use these calculations to find materials with very high mobility that may be competitive for 2D transistors. So what I'm going to do in the next few slides is to give you a kind of first an intuitive idea of what calculations of mobility are, and then give you a little bit of the math very quickly, and then I'll show you some data. So what is the mobility in a nutshell? So this picture on the left shows some atomic, an atomic structure, an idealized atomic structure of a crystal, for example. You might have an electron that travels here, and once in a while it gets scattered by maybe an impurity or a vibration or an interface. And on average, if there is no applied electric field, the electrons remains in place, meaning that there is no natural tendency to move, for example, left or right in this figure. If, however, you apply an electric field, what is going to happen is that in between 2 subsequent scattering events, the electron feels an acceleration given by the electric field, and this leads to a stretching of the trajectory along the direction of the field. So if you wait sufficient time, what you will find out is that the electron will have moved a little bit to the right in this picture, and therefore they will have acquired a velocity that we call the drift velocity. So in this case, what we call carrier mobility is simply the coefficient of proportionality between this velocity and the electric field. Okay, so it's just a way to quantify how fast you go if you apply an electric field. Now, down this is a cartoon picture, and the question is, how do people do calculations of this at the atomic scale? In principle, we would like to study every electron using quantum mechanics. So this is hopeless because we have something of the order of 10 to the 20 electrons in this kind of systems. So it's just not possible. So what we resort to is a statistic description of the problem, and this is done using the Boltzmann transport equation, which is the same thing that you would use for example, studying fluid dynamics if you want to do use a kinetic approach. In the Boltzmann transport equation, what we do is to simply ask how many electrons are sitting in a certain region of phase space, which would mean with a certain position and momentum at a given time. And then we solve the integral differential equation to find out how this distribution evolves with time. So this is a standard Boltzmann equation that you find in any textbook of statistical mechanics. Is not specific to electronics or to quantum mechanics. And the only thing we need to do is to try to find out what to replace in these expressions in order to perform calculations that can be compared to experiments. So what we do in our work is basically to neglect time dependence because we are looking for steady state current flow. We neglect space dependence because we are looking at transporting homogeneous semiconductor. So we retain this part where the change of momentum with time is given by the force applied to the electron. And this could be the electric field or a Lorentz force for the magnetic field. And then we will need to include some mechanism for scattering on the right-hand side. So that's basically what we try to solve here at the bottom left, so the bottom right. Now, so this is what would happen in a classical simulations if electrons were classical particles. So the problem is that electrons are not classical, they are quantum particles, and what happens in solids is that since electrons are quantum, only certain quantum states are allowed. Okay, so the quantum states, for those who are not experts in solid state physics, are usually described by diagrams looking like this. So this is called a band structure diagram. It represents essentially the pairs of energy on the vertical axis and momentum on the horizontal axis that an electron can have in a solid. And these dots, when you join them together, form some kind of spaghetti-like plot, which are the allowed energy states. So the game in the Boltzmann equation in solids is to determine how electrons occupy these energy levels. And just to simplify, what we can say is that in most semiconductors, where you have electron current, most electrons are sitting in a very narrow range of these band structures that I represent here as a red kind of highlight. So if I zoom in, what we will see essentially something looking like more or less a parabola. Red represents quantum states that are occupied. And what one can prove from standard solid state physics kind of textbooks is that the slope of these curves represent the velocity of the electrons in that quantum state. Now, what is the current? You can imagine from this plot the following. To find the current, I need to add the velocity of all the occupied quantum states, and that velocity will give me how fast and in which direction the electrons are moving. So here, I see that this distribution is symmetric. That means that half of them have positive velocity, half of them have negative velocity. So if I add this up, the current will be 0. And that's a standard case for a semiconductor without electric fields. If I apply an electric field, what is going to happen is that this distribution will be distorted. Basically, some electrons will acquire some additional velocity here. Some electrons will lose some velocity here. So the distribution will be slightly skewed. And as a result, if I add up the velocity of all these occupied states, I find that now I have a net current going towards the right. So that's how we compute electrical currents in response to electric fields. In practice, how do we do that? So more formally, for those interested in the formalism, we define the current as a weighted average of the electron velocity with the weights given by the occupation factors of given quantum states. Then you can define, from simple considerations, the mobility as essentially the variation of the current with respect to the electric field, in line with what I gave you, I said earlier about the intuitive picture of mobility. And if you combine these two relations, what you obtain is that we can compute the mobility by simply evaluating the linear response of the distribution function with respect to fields. And then this will be our weight factor in adding up all the velocities. So the goal of these simulations in practice is to determine how the distribution factor of electrons changes once you apply an electric field. And it is done using, go ahead.
So to get the intuition for this, a lot of what you're describing sounds a lot like a frictionless flow through a surface, because it seems like electrons do not interact. The mechanics follow a different formula from regular Newtonian mechanics, because you have that parabola, which is a different momentum kind of calculation. But other than that, it has that flavor of a frictionless flow. But it seems like there's complications that are missing.
Yeah, that's correct. So it would be frictionless flow. So if you had the 0 on the right-hand side in this picture, in this slide, you would have frictionless flow. That would be collisionless flow correctly. What I'm not showing in this intuitive picture is that, so what I showed basically, if you apply an electric field, you change this distribution. Okay. What you need to imagine is that this picture may not be static in the following sense. In the same way as I apply an electric field, some electrons start occupying these states. If I keep the field there and there is no other effect changing distribution, these electrons in red here will keep moving along this line. Okay, so they will just keep drifting right into this figure. In practice, these are not happen because there are scattering events or collisions that bring the electrons back to the left. Okay, so at some point there is a steady state where let's say the drift caused by the field and the equilibration provided by the scattering creates a static equilibrium distribution. Does it make sense?
It does. Now, what you're describing right now sounds a lot now more like a neutron transport, where you have to, like the fission reactor, where you have to like track particles and have them collide. But I get the flavor that you don't actually do that. You have some kind of a mass equation saying that when you have so much density at the state, there's a counter force that's like scattering goes up, you forces it back. Is it more like that?
That's correctly like that. It's exactly like that, actually. Yeah, yeah. In fact, the methods that you're using for, let's say plasma physics or neutron kind of transport, they're actually quite similar. Yeah. So
okay,
yeah. But,
and then the attributes of the material. So then do you have like lookup table kinds of things saying this material has the following like scatter threshold, or do you have to in your simulations model it live, like actually like explicit the terms for that?
Yeah, I'll show you that in the next couple of slides. So let's say the short answer is that there is no, the most important thing in all this is that there is no empirical parameter coming from experiments. So everything is calculated from quantum mechanics at the end.
Got it.
So let me show you how we do it. So basically, for most applications we're interested in, we're interested in a weak electric field, simply because that's the regime where these transistors operate. So instead of looking for the distribution function as a function of the electric field for any fields, we can just look at the first order term, when you apply the field. So it's just a Taylor expansion, right? So once you focus on this derivative, which is what we need for the mobility, the Boltzmann equation I gave you earlier simplifies quite a lot. So it becomes this object you see in the middle. So the left part is still the collisionless part. So this would be frictionless transport on the left. And what you see on the right is two components. One, you take electrons that are in a certain quantum state, and then you account for the probability that by some collisions, they may be scattered somewhere else in phase space. And then you take electrons that are sitting somewhere else in phase space, and you account for the probability that by collision, they may be scattered into the region of phase space you are now considering, okay? So you essentially have a drift term coming from the electric field on the left, an out-scattering term from the state you're focusing on to anywhere else, and an in-scattering term from anywhere else to the point you're focusing on. And that's a very standard concept in, classical kinetic theories. So where things get complicated, maybe I can also mention that this actually is a very simple problem to solve. It's basically a standard linear system, solution of linear system. The only complexity here is that the matrix, let's say A, that forms this, that you want to solve for, maybe a very large matrix, maybe 100,000 by 100,000 or 1,000,000 by 1,000,000, let's say. So these are very large matrices. Now, the problem actually is not really the solution of the linear system. Actually, this usually it's a very small part of the computation cost. So the problem in all of this is calculating these ingredients. So I put them in red now. So these epsilon and k are the energies of the electronic states. So these are the quantum states of the electrons. So one has to determine those. The v are the velocities, which are simply the slopes of these energy band curves. And these are fairly easy. What is difficult is these scattering rates from your state to somewhere else or vice versa. So these scattering rates essentially need you to take into account possible scattering mechanism. And for example, if a material operates at finite temperature, as is the case in every transistor we need, for example, room temperature, you will have lattice vibrations. So lattice vibrations are quantized, so that leads to phonons. So you need to include the fact that electrons might be scattered by phonons that are, kind of running around the system and may end up in different regional phase space because of that. So now this is what takes the most of the computing time, because these calculations are extremely demanding, and they scale with maybe n4, so where n is the number of atoms. So you can only do simulation for fairly small systems, okay? And this is something that has become possible maybe over the past 5 to 6 years. So before we couldn't do this completely from, let's say, first principles of quantum mechanics. Now, let me tell you just one slide of how people do calculation of these quantum states. There is a tool that is called density functional theory, which now is fairly popular. And I don't want to give you an introduction to DFT because that would take too long, but I just want to show more or less what is being done. So we need energies of quantum states. So what people do is to solve a Schrödinger-like equation. Okay, this is like solved in real space or in reciprocal space. We don't know the potential that the electrons are feeling, but we have a theory called density functional theory, which gives us a recipe on how to build this potential. So we usually start with some kind of guess for this potential. We solve the equation for the wave functions. From the wave functions, we square up to get the probability density, and then we sum up over all the occupied density of electrons. And then this theory tells us how to transform this density into a potential that all the other electrons are feeling, okay? And this potential, in the end, is used back into the original equation, and that's why it is called a self-consistent field. This basically means the field is generated by the electron wave functions and is consistent with the solution of this equation, okay? So in the end, it's consistent with itself. So this process is at the basis of all of the density functional theory approximation that we use today. Did you have a question?
Around this, yeah. What are the dimensions of the state space? I mean, like position, momentum, that kind of stuff.
So basically, you have to imagine that the wave function, the psi sub n, is a function in a three-dimensional space. So for example, that would be a box representing the unit cell of your system. It may be something like 5 angstrom, times 5 angstrom times 5 angstrom, or 10 by 10 by 10. Usually, you might have you will represent that using a Fourier transform, and you might have something of the order of maybe 50 to 100,000 coefficients, and that's really how this is solved. Does it make sense?
Okay, so the space still is a three-dimensional space. It's a position space, not a momentum space. But the challenge is that you still have to, well, first it's Fourier, so it's why is it Fourier as opposed to plain XYZ kind of a treatment?
Oh, that's just a matter of convenience. So it turns out that one could do both. During the past maybe 30 years, when all these techniques have been developed, it just came up that a Fourier treatment is more advantageous in the case of periodic crystals. Okay, and usually people use a representation, as you say, XYZ, mostly for systems that are not periodic. For example, if you have a nanocrystal in vacuum, so the boundary conditions of vanishing wave functions at the boundaries, so that you use Cartesian coordinates. But in this case, since you have a periodicity, so the crystal is essentially an identical repetition of an infinite repetition of identical units, you need to impose periodic boundary conditions. And with periodic boundary conditions, it's just more convenient to use a Fourier type of representation. Does it make sense?
Yes. So let me maybe ground this down. So if I was ignoring all quantum effects, I would think, I'm imagining two electrons, and the nastiness it's collisions with the atoms of the material, but it's the electrons are messing with each other. That's what I'm reading from this equation. Where you get one electron moving up and down, another equation is going to be affected by that force moving up and down, forcing the first one to be moving up and down. They're interacting.
Correct.
That, but with like millions of electrons.
Yeah. So so there is a simplification. That is the fact that what we describe really is a unit cell of the crystal. So for example, let's say in a silicon crystal, you would have only 2 atoms. You study these equations for 2 atoms, and then you apply boundary conditions, periodic boundary conditions, so that you effectively describe an infinite crystal, but you simplify the description using periodic repetition of these units. Does it make sense? So we end up having something of the order of 10 to 20 electrons at a time.
And they're interacting with each other, but you're assuming the same interaction over and over and over down the material.
Yeah. So basically, they interact with each other. So that's a very good point. So what density functional theory does is to simplify the way we take these interactions into account. So maybe just to give you an idea, so every electron wave function contributes to the electrical charge density. It will be this N here. Okay. So very simply, this charge density, for example, if you were to do a classical model, it would generate some potential, electrostatic potential via the Coulomb law, right? So this electrostatic potential is sitting down here. So that's one of the effects that the presence of an electron generates on all of the other electrons. Then there are other more complicated effects that are sitting into this other potential is called exchange and correlation. So these are quantum effects that go beyond the simple electrostatics. And essentially, for example, if you have a Pauli exclusion principle, that would be accounted for in this kind of potential and so on. So this is a way to deal with electrons one by one by solving these equations individually, but then coupling them through this potential that you see down here.
Okay, and then the Fourier bit, I'm inferring, is just that you don't really say this electron affects this electron. It's like this, when this electron vibrates at this frequency, this electron vibrates at that frequency for all frequencies.
Yeah, that's correct. So that basically would be the energy eigenvalue of each of the electron states. Yeah.
Right. It's good to say. When I say frequency, you say energy, and it's the same.
Yeah, it's the same. Yeah.
Got it. Okay, that helps a lot. Thank you.
Yeah, that's basically the energy or frequency, if you prefer, would be the eigenvalues of a very big matrix that is written in the space of coefficients of a Fourier transform. Essentially, that's what we usually do. Okay.
Okay.
And basically, from that we get the wave function, we get the energies, we get the momenta, we get the vibrations, and we get the scattering rates. So essentially, I'm not giving details, but there is a whole machinery that one can use to do that. And one thing I also want to mention is that the part of the story that is about density functional theory is something well established now. Just to give an idea, for example, here at UT Austin, we teach a class called density functional theory for first-year graduate students, and it's really something now that is accessible to most. There are books like this one written on the topic, so we do tutorial exercises. So there has been a lot of developments over the past 30 years to the point that many basic features can be done fairly simply even on a laptop. And this is about just density functional theory. Then transport calculations are much more advanced than the required supercomputing at this point. So let me just show you some results so that I get out of the kind of the bush of the mathematics. So this is just to convince you that these calculations are actually predictive. This is an experimental set of data for silicon, the most common semiconductor. You see the atomic structure on the right. So these are mobility measurements at a subfunctional temperature in a log scale. And what I'm going to put on top of that is the result of our calculations. So the red line, I would like to emphasize, is a set of components that you cannot see because there are many, but it is not a fit to the experimental data. In fact, the only two parameters that enter our calculations are the atomic number of silicon, meaning how many protons are in the nucleus, which is 14, and the atomic mass of the silicon atom, which is about 28 atomic mass units. So with these two parameters, we are at the point of essentially producing complex experiment on real materials almost exactly. Okay, so that's the level of accuracy that we can aspire to, at least for silicon. Now, the situation is not as good for other materials, so we did some benchmarking, and essentially, if you try to repeat the same for many other very well-known semiconductors, what you see is that the performance of this approach degrades slightly. So what you see in this slide is basically a comparison between experimental data on the vertical axis and calculations by us on the horizontal axis. And the vertical, so the horizontal, sorry, I'm sorry, the line of 45 degree would represent perfect agreement. So essentially, if our data points fall on this line here, it will mean that we are essentially exact compared to experiment. But as you can see, all our data points are slightly to the right of this. So on average, we make an error of the order of 30% over the calculated mobilities. And this is something that has been possible over maybe the last 3 or 4 years. Already a decade ago, this was just off by orders of magnitude, but we had an improvement in the methods that has been phenomenal. And now we are just 30% away, not perfect, but almost perfect at this point. And we know what's going on and why this, how this could be improved. It will take some time to get there. So why are we interested in this kind of benchmarking and trying to demonstrate that these techniques are predictive? Well, at the end of the day, what we want to do is to predict materials with high mobility. So this is an example of a very recent study of two-dimensional materials searching for high mobility candidates. So the way now these things are done is the following. So you look up for a database of hypothetical compounds. So for example, this materials cloud database contains structures for 5,000 compounds. And we want to calculate mobilities for most of them, but that's currently not possible because a mobility calculation may take maybe 3 or 4 days on maybe 40 nodes of a supercomputer, so that's too expensive to do all of them. So we proceed through a hierarchical screening where basically you start down-selecting materials based on features that are very easy to calculate. And as you go down this funnel, you start doing more and more complicated calculations. And at the very end, you deploy the most advanced Boltzmann Boltzmann transport kind of approaches to really be as predictive as you can. And on the right, you see just an example, the scatter plots we get for some of the properties, like this called are the electron effective masses, which are metrics for potential mobilities. So to make a long story short, the main outcome of this work was actually that we managed to predict that one of the most common 2D semiconductor, which is called tungsten disulfide, it has this kind of shape here with tungsten in the middle and sulfur at top and bottom, should have a mobility which is of the order of 1,000 centimeters square volt second. So this would be interesting enough to start thinking about this material as a possible replacement for silicon. And at this point, there were quite some interesting discussion with colleagues, because there were previous calculations that obtained something like 100, so much smaller than us, and also experiments, which is this gray bar, which was of the order of 100. So it seemed at some point that our calculations were way off experiments and previous work. So for the discrepancy with previous work, what we managed to demonstrate is that previous work that led to this kind of numbers did not take into account an important effect in these systems, which is called spin-orbit coupling. So what that is the fact that the spin of the electron sees the orbital angular momentum, and this leads to some forbidden scattering processes. And as a result, the electron experiences less scattering if you incorporate correctly the spin orbit in this material. I won't go into the details, but it's just to say that if you do a more sophisticated calculation, you may get results that are very different from what was found already 2 or 3 years ago. And then what remains is the question of why our calculations are so different from the experiments, which are down here in the gray. And actually, while we were publishing our work, there was a really good work by a very famous group in Harvard, so the group of Philip Kim, who managed to make semiconductors of this type with extremely low levels of impurities, so essentially extremely pure materials, and they managed to demonstrate mobilities of the order of 1,000 centimeters per square volt second. So essentially, these experiments that happened at the same time as our prediction confirm indirectly what we've been predicting. And what that demonstrates is essentially that even if a material maybe has been discarded because some experiments show that the performance was very poor, maybe if calculations indicate that the potential is very high, maybe one should look back at these materials, trying to improve the manufacturing, trying to make them, maybe less, trying to improve the quality of the samples and perform very accurate measurements and check whether they could deliver much higher performance than what one thought. So at this point, we believe that these kind of materials are now extremely promising for what could come, in the future for 2D electronics, and we are part of a consortium with experimental collaborators. We're trying to work out whether one can make devices and deliver this kind of performance that we are predicting. So if I have a couple of more minutes, Greg, let me just go over something about software, just to give you an idea. So all of we do is based on open source software. We develop a software called EPW, which is actually part now of a much bigger platform called Quantum Espresso. So just to give you an idea, this is Fortran 90/MPI/OpenMP. It's something on the order of 100,000 lines of code. There are maybe about 1,000 users at this point of this software. So we have a forum, we have a documentation online, and essentially we're trying to this operation is growing, and the number of people developing this software is also growing. So now we have about 5 groups developing it. The lead developer is one of the research scientists here at UT Austin, is Dr. Sabyasachi Tiwari, and the names you see here are basically all the developers of this software project. And there is a lot of interest also on our side to educate the community. So we work in partnership, for example, with the National Science Foundation and Department of Energy to deliver schools and training for people both in the US and abroad. And this is just some big photograph from the school that we organized recently, maybe in June here at UT Austin. And from the numbers down here, you can tell that the demand for this kind of techniques actually is growing quite a lot, has been growing quite a lot recently. Finally, where we're going, so the codes now are being ported all to GPU. Clearly, most of the US supercomputers are moving towards GPU, so we need to be ready for that. And we've been doing a lot of work to refactor the codes for that. So this has been done by Dr. Taiyun Kim in my group, and there is a significant speed up we are obtaining from this. So this is probably going to be the future of the software that we're developing. And another thing we're doing is to try to make it easier to run this complex calculation. So we work with the Texas Advanced Computing Center with the National Science Foundation to basically deliver all of these technologies on the cloud. So at this point, we are able to let users, any users, run directly on large supercomputers by basically logging in on a web browser and using Jupyter notebooks and deploying essentially high-performance computing calculations directly from the browsers, which is something quite novel at this point in this space. Finally, if somebody was to ask me, were to ask me where this is all going, I think there is a fair chance that over the next 5 to 10 years, we might be able to move to complete device simulations. So we are getting to the point of reaching extremely accuracy as compared to experiments, even experiments that don't exist as yet. So for materials that have not been invented yet. So this is very good for screening and for accelerating the pace of materials discovery. And to answer the question I asked at the beginning of the talk, whether one can make transistors or design them one atom at a time, I think that a fair answer is that we are really getting there. I know there is increasing interest in this kind of simulations, also from industry. And I think this may be a game changer, maybe once we can deliver predictive accuracy, not just for materials, but for entire devices, including LED, leads, contacts, substrates, and so on. And this is actually work that is currently in progress. And the last slide is about, just acknowledging that all of the things that I've said have been done by a group of brilliant young researchers. So that some of them are in this picture, and the work would not be possible without them. And also, we are grateful to all our sponsors that support this research, from software to engineering. And with that, I will close the presentation, and I'm happy to take any other questions.
Yeah, thank you very much. One, a clear question is you focused on all the details you have to account for. In order to make a little calculation in comparison, let's say your method for that material and the alternatives, which didn't cover all the details. But another thing I noticed is you have the multi-resolution simulation, where you do many cheap calculations of low priority materials and expensive calculations of high priority materials. But clearly your space is so stiff, I guess, that you can easily miss a promising material if you use a low fidelity calculation. So how do you deal with that tension?
Yeah, that's an extremely good point. Let's say that, so this goes back to, I guess, this approach. So actually, you raise a good point, and I'm not totally happy with this approach. So this is something that, is very common at this point for materials design. Let's say the philosophy is the following. So that is the following. Experimentally, it is just impossible to screen 5,000 compounds and make devices for all of them, okay? And just making one of them is extremely expensive and time-consuming. So the idea the philosophy here is that if out of 5,000, you could propose 3 or 4 that are viable, and one of them works, you would have saved an enormous amount of resources, okay? Now, obviously, this does not guarantee that all of the others that you might have discarded may not work. And that's actually something we see coming back, over and over again. So we are actually now working on a different philosophy, which would be essentially trying to perform all of these calculations at the kind of highest possible accuracy directly using some clever automation strategies. And this is something that is currently in progress in our group. But I agree that ideally, we would like to compute, for example, Boltzmann transport for all of them. And I think this will become possible, maybe not tomorrow, but in a couple of years, that should be feasible, because the methods and the performance are improving dramatically. Just to give you an idea, already by using GPUs, we're going to go 10 times faster than what we currently do, okay? And by accelerating some of the algorithms, we can gain another factor of 10 to 100. So some of these things will become much, much easier over the next few years. Yeah.
So, okay, so now you're pointing to using modern, well, I guess more structured compute like GPUs. In fact, actually, on that note, because this is a very classic way of improving algorithms, you use new hardware more effectively. So to what extent can like low precision architectures, like 16-bit multiplication, which has limitations, but at least you can get many, many more flops that way in a more structured format. To what extent does that hardware help you?
Yeah, that's an extremely good point. So actually, we are looking to that. Basically, at this point, we don't know. So, I mean, it's a game of optimization, right? So, in order to, for example, to figure out what we need to accelerate, essentially, in this case, Tayun has been using the HPC toolkit to find out the the bottlenecks. And I think in the same way, what we have to do is to basically trying to use single precision in some components of the code and see what is the impact on the final numbers. I suspect that there is a lot of room for improvement. The philosophy until a few years ago was just you try to implement the physics, the equations that you need, and you try to deliver some meaningful answers. Codes were not very reproducible or verifiable, or validation was not a thing. Now, the tools to develop are so much more powerful that all of these things can be done, and we have much better control on the software base. So that's why we're doing an effort in refactoring. And I think, I guess, I don't have data now to back this up, but I guess things like single precision also would be useful in the future, because we are probably wasting a lot of flops by just trying to have the highest precisions everywhere, just in case, but it's not needed.
Got it. And then, so what I'm sensing now is you want to have all the physics, but maybe not at full precision. And if that's the case, to what extent, like a machine learning, like neural surrogates of the right physics, but now it's if I can summarize neural surrogates, it's lower precision, but in a more sophisticated way than simply lower precision. To what extent is that going to be constructive?
Yeah, that's also another area of interest. So let's put it this way. We are doing some work on to have a foothold into that space, but that requires data, right? Mm-hmm. A lot of data, and at this point, calculation, for example, of transport that we are interested in. So those kind of calculations, maybe we have 20, 30, 40, 50 data points, if you want. So it's not enough for training kind of serious models. So where training is being used now, for example, is studying, atomistic model of structures, for example. So instead of using full density functional theory calculation, which are expensive, one could attack large systems by training density functional theory on smaller systems, and then deploying these models on large systems. And that's what we are actually doing at this point. For more advanced properties, I think we need to generate the data. Okay, so we will need to contribute to databases and increase the number of calculations one can do in this space by a few orders of magnitude before we can meaningfully think about surrogate models or anything in the space of machine learning or neural networks or something like that. But really, data is the main priority, I would say, at this point.
Okay, makes sense. You have to. So, is your data set like given the input, here's the output, or is it more like I'm thinking like a weather model where you have a bunch of intermediate states and you have points in the coordinate, in your state space, as there's like a 3D picture, but a Fourier space picture?
So the point is that depends on what one is calculating. For example, if if I go back to so this kind of expressions like the Boltzmann equation. So what you need, all these ingredients essentially. So the energies, velocities, scattering rates, and all that. So you can imagine this as being a gigantic vector or feature, and then you could map the structure of the material to this feature. The problem is that this mapping will require many more data points that we currently have. Mm-hmm. And one could also map structure to mobility, for example. Just you have a structure to start with, and you predict a number. That's probably easier. What people have been doing so far, and they are pretty successful at it, and we are also working a little bit on that, is that if you see this density functional theory, let's loop, at the end of the day, this gives an energy for a given structure, okay? And it requires a lot of solutions of partial differential equations. So one could completely bypass that by mapping the structure to energy by considering many, many structures. So just to give you an idea, if you want to get the energy of a silicon crystal, in this way, you may need a few thousand or tens of thousands of calculations of this type in order to train a model. Mm. So that gives you, I guess, the the size of data sets that we will need. And it's only for the energy. So properties are more complex, like mobility, they may require more data points. And we don't know how much. That's clearly an open question at this stage.
Got it. That helps a lot. Well, yeah, thank you very much. It was fascinating. Yeah, thank you for joining us.
Okay, thank you so much.